Trig, unit circle. So in this video what we're going to be looking at is what is the unit circle and how can we use it to find our trig ratios. So a unit circle is a circle that has a centre of 0, 0 and it has a radius of 1 unit in length. Hence the name unit circle. So if we look at this circle that's drawn here, if I was to mark in the centre, that would be this point here, 0, 0. And if I was to draw any point along the circumference of the circle, well, from our coordinate geometry, we would say that I have gone out a distance of x on the x-axis and up a distance of y on the y-axis. Now, if I was to move this point anywhere along the circumference of the circle, what happens is that with respect to the x-axis, an angle is traced out. So this is the angle here that is being traced out. And we always move in an anti-clockwise direction along the circumference when we're tracing out our angles. So in other words, that angle would start at 0 degrees and it would go around one full circle, would be 360 degrees in full rotation. And we'll look at our angles in a second. So for the moment, if we focus on this little triangle that I've traced out, it is a right angle triangle because I've gone out a distance of x on the x-axis and I've gone up a distance of y on the y-axis. The distance from 0, 0 to the point xy or anywhere on the circumference is 1 unit length. So let's have a look at this a little bit closer. Because this is a right angle triangle and I've marked in my angle, then the side opposite the angle is our opposite. The side opposite the 90 degrees is our hypotenuse. And the remaining side beside the angle is our adjacent. So what I can actually say is that I know sine theta is the opposite over the hypotenuse. And therefore from this right angle triangle, that means that sine theta is the opposite side, which is y, over the hypotenuse, which is 1. In other words, my y coordinate will always represent sine theta. Now if I do the same for cos, well, cos theta is the adjacent over the hypotenuse. And again, if I look at that right angle triangle, well, the adjacent is x. And the hypotenuse is 1. In other words, the x coordinate is always going to be represented by cos theta. Now another one to note then is the relationship between both sine and cos. So I can say, well, I know tan theta is the opposite over the adjacent. And of course, if I go up and have a look at what the opposite and the adjacent are in this right angle triangle, well, I can see the opposite is the y and the adjacent is x. So that means that I can say that the opposite is y and the adjacent is x. But of course, y is sine theta and x is cos theta. So we have our first relationship there, that tan can always be found by dividing sine theta by cos theta. And if we go to our maths tables, page 13, we can see this relationship on the top of page 13. Tan is equal to sine over cos, but also we can see then that this x coordinate on the unit circle going in an anti-clockwise direction is given by the x coordinate cos A and the y coordinate sine A. So in other words, if I go back up to my diagram here, cos will always be the x coordinate and sine will always be the y coordinate. Okay, so if the unit circle has a radius of 1 and a centre of 0, 0, and when starting at reading our angles, we always start at this coordinate here on the x-axis, and we move in an anti-clockwise direction, where the coordinate that I've just marked on my unit circle, I've gone out a distance from the centre of 1 unit, because the radius is 1, and I've gone up a distance of 0. And as I move in an anti-clockwise direction. Then this coordinate here, 1, 0, is going to represent 0 degrees, because I haven't actually traced out any angle yet with respect to the x-axis. As I take that radius and I begin to move it along the circumference, what happens is I trace out an angle, and that angle grows as I move further and further away from the point 1, 0, until I get to this point here, which is out to 0 and up to 1. In which case I have now moved in an anti-clockwise direction from 1, 0, an angle of 90 degrees. As I continue to move along the circumference, going beyond 90 degrees, well, now what's happening is as I move back onto the x-axis, I reach the point out to -1 and up to 0. I have now moved an angle of 180 degrees along the circumference back to the x-axis. If I continue past that point, and again, taking that point and moving it along the circumference, the angle continues to grow. And now when I reach this coordinate here, out to 0, and down to -1, I have now traced out an angle of 270 degrees. And as I continue along the circumference and I keep going, I end up back where I started at the point 1, 0. In other words, I have now gone one full revolution, which is 360 degrees. So in other words, one revolution from 1, 0 back to 1, 0 is 360 degrees, or 2 pi if we were talking radians. So let's remove all of those lines. And if we just focus on those 4 points where I've moved 90 degrees, so from 1, 0 to 0, 1, and from 0, 1 to -1, 0, and from -1, 0 to 0, -1, and from 0, -1 back to 1, 0. I can see I've moved 90 degrees each time. Now, what's interesting about these coordinates is we know from the previous slide that the x is always cos theta and the y is always sine theta. So if I look here and if I just write it in green, we know that the x is always cos and the y is always sine. So I'm just going to write cs over the x and s over the y, c over the x, s over the y, c over the x and s over the y. So we can actually use this unit circle, and looking at these 4 points, we now have information about cos and sine for 4 different angles. In other words, if I look at the first angle there, I can say, well, cos of 0 degrees is the x-coordinate, which is 1. Sine of 0 degrees is the y-coordinate, which is 0. And therefore, tan of 0 degrees is sine of 0 over cos of 0. As again, if we go back, we established that tan was sine divided by cos. And therefore we can say that tan 0 must be sine 0, which is 0, divided by 1. In other words, tan of 0 degrees is 0. And of course, if you go and check on your calculator, and making sure your calculator, of course, is in degrees here, you will see that if you type in cos 0, sine 0, and tan 0, you'll get the answers 1, 0, 0. In other words, your calculator has been programmed based on this unit circle. So now I can do the same for 90 degrees. And I can say, well, if I get cos of 90 just by looking at the unit circle, sine of 90 just by looking at the unit circle, cos of 90 is the x-coordinate, and the x-coordinate is 0, and the y-coordinate is 1. So cos of 90 is 0 and sine of 90 is 1. And therefore, if I get tan of 90, it's going to be sine 90, which is 1, divided by cos 90, which is 0. But 1 divided by 0 isn't possible. So we say that tan of 90 is undefined. If I do the next one there, 180 degrees, well, we have cos of 180 is the x-coordinate, which is minus 1. Sine of 180 degrees is the y-coordinate, which is 0. And therefore tan of 180 degrees is sine, which is 0, divided by minus 1. In other words, tan of 180 degrees is 0. And then if I go back to 0 minus 1, we have 270 degrees. So we can say cos of 270 degrees is the x-coordinate, in other words 0. Sine of 270 degrees is the y-coordinate, which is minus 1. And then tan of 270 degrees is sine divided by cos. So again, we have another case where tan is undefined. So tan is undefined at both 90 and 270 degrees. So we didn't even have to use our calculator or our maths tables. We can literally just look at the coordinates to find out what are the values of cos, sine or tan of any angle on our unit circle. So if we look at the unit circle, we can see it's clearly divided into 4 sectors, where the first sector goes from 0 degrees to 90 degrees, and we call this the first quadrant. The second sector goes from 90 degrees to 180 degrees, remembering that we're always going in an anti-clockwise direction, and we call this the second quadrant. The third sector goes from 180 degrees to 270 degrees, and we call this the third quadrant. And then the fourth sector goes from 270 degrees back to 0 degrees. In other words, we've gone 360 degrees in total. And this is our fourth quadrant. And because it's a circle and we're going in an anti-clockwise direction, if I keep going around a second time, a third time, a fourth time, all we keep doing is adding on 360 degrees each time. In other words, a second revolution would bring me back to 720 degrees, and so on. So we're going to look a little bit closer at the relationship here between the first quadrant, second quadrant, third quadrant, and fourth quadrant. So what we're going to do is we're going to take our protractor, and we're going to use our protractor to measure out the angles 30 degrees, 150 degrees, 210 degrees, and 330 degrees on our unit circle. So if I put my protractor down at 0 degrees, and I mark in 30 degrees, that's this point here. And then if I mark in 150 degrees, that's this point here. And if I do the same for the next angle, it's 210. That's the point there. And then 330, this point here. Okay, so let me get rid of this protractor. And what we're going to do next then is draw the right angle triangle, which marks out each of these angles. So there's 30 degrees. So I'm going down. And I've gone out. So what we can see is we're going to mark in the hypotenuse, the opposite and the adjacent for each triangle. So I'm going to focus on one at a time. So here's 30 degrees. This one was 150. This one was 210. And this one was 330 degrees. Okay, so if I mark in each side of the triangle, we know it's a unit circle. So that means the hypotenuse is 1. And I can see here, if I read off the x-axis, that I've gone out approximately 0.8, that's halfway across to be 0.9, so it's almost just past 0.8, so approximately 0.86 is that distance here. And I can see I've gone up halfway between 0.4 and 0.6, so that's 0.5. From the x-axis up. So in other words, the coordinate that's marking out this angle of 30 degrees is out to 0.86 and up to 0.5. So if I do the same for 150 degrees, what you can see is that I've gone 150 degrees from the coordinate out to 1, 0, traced it all out. But because this angle here is 130 degrees, then in my right angle triangle, the angle is actually 150 minus 180, or 180 minus 150, I should say, which gives me 30 degrees again. Now, if I mark in my opposite, my adjacent, and my hypotenuse again, well, the hypotenuse is 1, and I can see I've gone out a distance again of 0.86, this time in the negative direction, and I've gone up a distance of 0.5 again. So in other words, if I go across and I go down, again I can see it's the same distance. If I do the same for 210 degrees, again, I have rotated along the circumference of the circle an angle of 210 degrees, but from the x-axis, I've actually dropped down the difference between 180 and 210, which is 30 degrees again. And again, if I look at the values of the opposite, the adjacent, and the hypotenuse there, again, I can see my radius is 1. I've gone down 0.5 on the y-axis, this time in the negative direction. And I've gone out 0.86 again. And again, if I go to 330 degrees, well, I've rotated 330 degrees from the point 10 in an anticlockwise direction, but with respect to the x-axis, well, it's 30 degrees again. In other words, if I go full rotation, that's 360 degrees. So to get from 330 to 360, it's an angle of 30 degrees. And again, if I look at the sides of my triangle, I have gone down a distance of 0.5. In other words, there's 0.5, and I've gone out a distance of 0.86 again. So even though we have traced out 4 different angles there, 30 degrees, 150 degrees, 210 degrees, and 330 degrees, what we can actually see is that the sides of the right angle triangles all have exactly the same lengths. So if I look at each of those coordinates, remembering that the x-coordinate is always cos and the y-coordinate is always sine, well, I can write down the coordinates for each of these angles. So 150 degrees, well, I've gone out on the negative direction of the x-axis, so I've gone out a distance of minus 0.86, and I've gone up a distance of 0.5. For 210 degrees, I've gone out in the negative direction for x, so out minus 0.86, and I've gone down on the y-axis a negative direction of 0.5. For 330, I've gone out a distance of 0.86 in the positive direction, and I've gone down on the y-axis minus 0.5. So again, marking in the x is cos, the y is sine, the x is cos, the y is sine, the x is cos, and the y is sine. Well, something interesting happens here. So in other words, if I'm looking at number 4 here on the left, if I write down the value of sine, cos and tan for each of our angles from these coordinates, I can say, well, sine 30 is 0.5, cos 30 is 0.86, and remembering that tan is sine divided by cos, so if I use my calculator and I get 0.5 divided by 0.86, I get approximately 0.57. If I get sine 150 from my coordinates there, so sine is the y coordinate, so that's 0.5, cos is the x coordinate, which is minus 0.86. And again, if I divide sine by cos, I get tan 150 is minus 0.57. And then if I look at 210 degrees, sine of 210 degrees is the y coordinate, which is minus 0.5. Cos is the x coordinate, which is minus 0.86. And tan is sine divided by cos, so minus divided by minus is plus, which is 0.57. And then the last one there, 330. So sine 330 is minus 0.5. Cos 330 is 0.86. And tan, again, sine divided by cos, so negative divided by positive is negative. So that gives me minus 0.57. So what we should notice there is that all of the values are the same for all the sine. So sine 30, sine 150, sine 210 and sine 330, I get the same number. The only thing that's different is the sine. And I can say the same for cos and for tan. The numbers are all the same for cos of each of those angles, and only the sine is changing. So what the angles have in common is that they're all the same value with respect to the x-axis. In other words, they're all 30 degrees with respect to the x-axis. And then what does this tell us about sine, cos and tan for each quadrant in the unit circle? Well, basically, if I get any value for cos in the first quadrant, well, it's always the x-coordinate. And the x-coordinate in the first quadrant is always going to be positive. But I can also say the same for sine and for tan, because x and y are always going to be positive in the first quadrant. In other words, I'm going out in the positive x direction and up in the positive x direction. If I look at the second quadrant, well, I can say that cos is negative, but sine is positive, and tan is sine divided by cos, so a positive number divided by a negative number is always going to be negative, and that's in the second quadrant. And that's again because if I look at the xy coordinate, I'm going out in the negative x direction and up in the positive y direction. If I look at the third quadrant, well, I can say cos is negative because I'm going out in the negative x direction. Sine is negative because I'm going down in the negative y direction. And tan is going to be positive because a negative divided by a negative is always going to be a positive answer. And then in the fourth quadrant, I can see that cos is always going to be positive because that's going out in the positive x direction to get to the fourth quadrant. Sine is always going to be negative because I'm always going down to get to a number in the fourth quadrant. And tan is a negative number divided by a positive number. So that means that tan is always going to be negative in the fourth quadrant. So it doesn't matter what point I plot, or in other words, what angle I trace out, depending on whether I've gone out in the x direction or up in the y direction, that's always going to tell me whether cos, sine or tan are positive and negative. So we can summarise this by looking at whether they're positive or not. In other words, in the first quadrant, I can see that they are all positive. In the second quadrant, I can see that only sine is positive and cos and tan are negative. In the third quadrant, I can see that tan is only going to be positive. And in the fourth quadrant, I can see that only cos is going to be positive. So in other words, if we go back to my previous slide here, what I can say is that they are all positive in the first quadrant. And this is always referred to as the reference angle, because an angle in the third or fourth quadrant or the second quadrant is always going to be the same as the angle in the first quadrant. So in other words, we traced out 150 degrees, 210 degrees, 330 degrees, but they were all the same as 30 degrees, which was the angle in the first quadrant with respect to the x-axis. In the second quadrant, I can say that they are only sine is positive. In the third quadrant, only tan is positive. And in the fourth quadrant, only cos is positive. So sometimes the easy way to remember that is that sometimes we say that it's all so terribly confusing. Hopefully not by the end of the chapter though. So A, S, T and C. So to work out our angle in the second quadrant, we always refer back to the reference angle, which is theta. So it's 180 minus theta. So in other words, we saw that 150 degrees, if I take it away from 180, I get my reference angle of 30 degrees. In the third quadrant, we were able to see that it was theta minus 180 degrees. In other words, 210 degrees is what we traced out. If I take it away from 180, I get 30, which is the reference angle. And in the fourth quadrant, it was 360 degrees minus theta. In other words, we traced out 330 degrees, and if I take that away from 360, again, I get my reference angle of 30 degrees. Now, the third quadrant is the only one where if I had it the other way around, if I had the reference angle and I want to know what is the equivalent angle in the third quadrant, then I would add it on to 180. So in other words, 30 degrees plus 180 gives me the angle in the third quadrant. Okay, so let's have a look at how can we use this to evaluate different angles using our unit circle only and not using our calculators. Okay, so we're going to find the following angles within our surd form, and we're not allowed to use our calculator, but we can use page 13 in our maths tables. So in other words, we're going to look at our special angles, 30, 45 degrees and 60 degrees. And using the fact that we know that in the first quadrant, this is our reference angle. And the second quadrant, the relationship is 180 minus theta and sine is positive. In the third quadrant, only tan is positive and theta minus 180 degrees is our relationship. And in the fourth quadrant, only cos is positive and 360 degrees minus theta is our relationship. So to find the value of cos of 135 degrees, we have to look at how are we going to do this. So what are our steps going to be? So the first step is to identify which quadrant is the angle lying in. Our second step then, after we've identified the quadrant, is to note if the trig ratio is going to be positive or negative. Once we've done that, we're then going to apply the quadrant rule to find the reference angle. And then all we have to do is use page 13 to write down the answer with the correct sign. Okay, so the first one's cos of 135 degrees. So 135 degrees is between 90 degrees and 180 degrees. Therefore, it lies in the second quadrant. We then look at the sine. So I can see that only sine is positive in the second quadrant. So that means that my answer for cos is going to be negative in the second quadrant. we need to find our reference angle. So it's 180 degrees minus theta is the rule. So 180 degrees minus 135 degrees gives me the reference angle of 45 degrees. So now if I look at 45 degrees for cos on page 13, well, there's 45 degrees cos, we go across and down, and the value is 1 over root 2. So in other words, cos of 45 degrees has a value of 1 over root 2, which then tells me that cos of 135 degrees is going to be the same value. The only thing that's different is the sign. Because it's in the second quadrant, cos is negative. So all I've done is used my unit circle on page 13 of my tables, and I have my answer. You can also check this on your calculator to see if you're correct. But as I said, we are not allowed to use our calculator to write down an answer. We have to go through the process of identify the correct quadrant, the correct sign, the reference angle, and using page 13 in your tables. Okay, so the next one is sine of 330 degrees. So our quadrant is the first thing we identify, which is the fourth quadrant. I can see that only cos is positive in the fourth, so that's telling me then that sine has to be negative. My rule is 360 minus theta. So 360 degrees minus 330 degrees gives me a reference angle of 30 degrees. So in other words, if I was to get sine of 30 degrees as my reference angle, and again I go to page 13, my tables, I'm looking for sine this time, and I'm looking for 30 degrees. So if I go across and down, I can see this time the answer is a half. But then if I refer to my quadrant rule, sine of 330 degrees is going to give me the same value, but a different sign. So the sign is negative for sine 330. So the answer is going to be minus a half. If I look at the next one, we have tan of 210 degrees. So 210 degrees is the third quadrant. And if I look at the third quadrant, I see that tan is positive in the third quadrant. My rule for the third quadrant is going to be theta minus 180 degrees to find the reference angle. So in other words, 210 minus 180 degrees gives me a reference angle of 30 degrees. Therefore, using the reference angle of tan 30, I'm going to page 13 in my maths tables. I'm looking for tan, looking at 30, go across and down, and I see my answer is 1 over root 3. Sorry. And therefore that means then that tan of 210 degrees is going to be 1 over root 3, and it's also going to be positive because tan is positive in the third quadrant. Okay, so the last one then is an interesting one, which is sine 660. So 660 is interesting because clearly the angle this time is greater than 360, which means I've gone around the circle more than once. So how many times have I gone around? Well, in order to figure out what is 660 degrees the equivalent to, all I have to do is keep subtracting 360 degrees. So if I go 660 minus 360 degrees, that's the equivalent of 300 degrees. So in other words, 660 degrees is going to be the same as 300 degrees, which is the fourth quadrant. And in the fourth quadrant, sine is negative. And therefore, 660 degrees is going to be exactly the same as finding the angle 60 degrees. In other words, my reference angle is 60. Sine of 60 from page 13 in my maths tables. Well, I go sine and I go 60, I go across and I go down and I get root 3/2. So even though I've gone around the circle more than once, I just keep repeating myself because these are periodic values. So therefore sine 660 degrees is going to be the same as sine 60, but in the fourth quadrant, so it's going to be a negative value. So if I was going around more than once or twice or three times, I just keep subtracting 360 degrees until I get back to the angle that's in either the first, the second, the third, or the fourth quadrant. Apply your quadrant rules and use page 13 to find your answers.